Hello viewers, I Dr. Mala Das Sharma welcome you to my video number 132 of my channel MALACHEMPHILIC. And video number 132 is the episode number 71 of Chemical Thermodynamics, where the topic is excess functions of non-ideal solution. So let's start. So thermodynamic excess function of non-ideal solution. See, this deviation from this ideal behavior can be best expressed in terms of excess thermodynamic function. That means deviation from the ideality we can best expressed in terms of thermodynamic excess function, which gives more quantitative idea about the nature of the molecular interaction. Now, excess thermodynamic function, say Y is a thermodynamic property. So excess thermodynamic property, which will be denoted by that property and then superscript E. So here excess thermodynamic property Y, that is the difference between this mixing, means change of that property during mixing while preparing the real solution, and the change of the property during mixing while preparing the ideal solution, okay, at the same temperature and pressure. So difference between the thermodynamic function of mixing for a real system and corresponding value for an ideal system at the same temperature and pressure is called thermodynamic excess function, and it is denoted by that function, that is symbol of that function with superscript E. Now coming to the expression of different excess thermodynamic function. First one is excess chemical potential, which is denoted by mu E. So as per the definition, the excess chemical potential will be is equal to chemical potential of the ith component for the real system, that means real solution, minus chemical potential of the ith component for the preparation of ideal solution. Right? Now, this chemical potential of the ith component in the real solution, we can write it as chemical potential in the standard state, which is, we can consider it as a pure state at the same temperature, plus RT ln activity of the component. Now, chemical potential of the ith component in the ideal solution, that will be is equal to this, again the chemical potential in the standard state, or here it is pure state, then minus RT ln mole fraction of the ith component. The standard state is identical for this real and this ideal solution. So this mu E, excess chemical potential, that will be is equal to RT ln activity of I minus RT ln mole fraction of I, and we know that this AI activity divided by mole fraction, that is equal to activity coefficient gamma I, which denotes the deviation from ideal behavior. So what we can write, mu E is equal to this RT ln AI by XI. So this is RT ln gamma I. Now coming to the next function, that is Gibbs free energy. So this excess Gibbs free energy, that will be the change in the Gibbs free energy during mixing for the preparation of real solution or non-ideal solution. So delta G mixing for this real solution, 1 minute, delta G mixing for real solution minus change in the Gibbs free energy during mixing for the preparation of ideal solution. So delta G mixing of this ideal. Okay. Now we know the expression of delta G, that is Gibbs free energy of mixing, that is equal to, this is your RT, then summation of Ni, ln, then Xi. Xi is the mole fraction, but for the real solution, here we have to take it as AI, that is the activity. Okay, then minus RT, then summation of your Ni, then ln, here it will be mole fraction ln of Xi. Okay, so what we can write? Excess free energy function, that will be is equal to, I can write it as RT summation of Ni ln Xi plus RT summation of Ni ln gamma I, because we know that AI is equal to activity is equal to gamma activity coefficient into mole fraction. Okay, so these things. And then minus this RT summation of Ni ln Xi. Okay, so RT summation of Ni ln Xi, this is getting cancelled. So it is excess free energy function will be is equal to RT, then summation of Ni ln, then gamma I. For binary solution, that means for two component. So for binary solution, what can I write? This I can write G will be is equal to RT, then N1 ln X1 plus N2 ln X2. Oh, sorry, not X, this is gamma. N1 ln gamma 1 plus N2 ln gamma, this is ln, N2 ln gamma 2. This is the expression of excess free energy function for the binary solution. Okay. Now coming to the excess entropy. Excess entropy. Here I have written this already. I have written the expression of excess free energy function for binary solution, which just now I have derived. Okay. Now we know that dg is equal to vdp minus sdt. So what we can write? Dol g, that is differentiation of g with respect to temperature at constant pressure, that will be is equal to minus s. So what we can write? That this minus excess of entropy, okay, is equal to, that will be is equal to dole of excess of free energy divided by dole T at constant pressure. So what we can write from here? We can write excess entropy, that will be is equal to minus dole excess of free energy divided by dole T at constant pressure. Right? So SE, that is excess entropy, this one, what can I write? This, say for binary solution, this one I have to differentiate. So this is, say it is minus this R is there, okay, then inside there are two terms, one is T and another one is this full terms, that means your N1 ln gamma 1 plus N2 ln gamma 2, okay, then by dol T, sorry, here I have to write dol, or one thing, I write here dol N1 is gamma 1, then T I write here, divided by dol T at constant pressure. Okay. Now we have to differentiate. There are two terms, this term and this term. Okay. So this, if I consider this is the first function, then SE, excess entropy, that will be is equal to here minus R minus RT, then here N1 dol ln gamma 1 divided by dol T at constant pressure, this is N1, plus N2, then dol ln gamma 2 by dol T at constant pressure, then by minus, then it will be equal to R. Okay, minus R, then this will be is equal to N1 ln gamma 1 plus N2 ln N2 ln gamma 2. See how we have done it. This differentiation is, there are two terms. So first function is kept as it is. Differentiation of the second. So second is N1 dol of ln gamma 1 divided by dol T at constant pressure. This is ln ln gamma 1 by dol T at constant pressure plus N2, because this N1 N2 constant, no, then dol of ln gamma 2 by dol T at constant pressure. So first function, differentiation of the second, then your second function is this one as it is, differentiation of the first, that is ddt of T is equal to 1. So this is the expression, sorry, here minus is there, no, minus R. So this is the expression for the excess entropy, right? Now coming to the excess enthalpy. Okay, already I have written this excess free energy function expression and excess entropy expression for the binary solution. Now we know that G is equal to H minus Ts. So what we can write? We can write that H is equal to G plus Ts. So therefore what we can write? Excess enthalpy, I can write it as excess free energy function plus T excess entropy, right? So excess free energy function, say for binary solution, I am writing that expression is there, and then entropy expression is there. Just we have to put the expression. So what it will be? Then your then your excess enthalpy, that is He, that will be is equal to RT, that means G excess, this one, excess free energy. So it is RT, then N1 ln gamma 1 plus N2 ln gamma 2 gamma 2, then it is coming as minus, this is minus sign is there, no? So it is minus RT square, then these things, N1 dol ln gamma 1 by dol T at constant pressure plus N2 then dol ln gamma 2 by dol T at constant pressure minus RT then N1 ln gamma 1 plus N2 ln gamma 2. So this is the expression. That is here G plus Ts. G is which one? This is this one. RT N1 ln gamma 1 plus N2 ln gamma 2 plus Ts. Okay. T have to multiply by T. So this is RT. So RT square minus RT square. Then this expression, that is this entropy expression, means excess entropy expression I have written. Okay. This one, full expression I have written. And then here also multiplied by T. Now what is happening? This one and this one is getting cancelled. So what is left over then? Left over is excess enthalpy. My leftover is this part, only this part, that is minus RT square, then N1 dol of ln gamma 1 by dol T at constant pressure, then plus dol of ln gamma 2 by dol T at constant pressure. So this is the expression. Okay. So excess, I'll just put it in square bracket. So this is the expression for excess enthalpy, and we have taken it for binary solution. Okay. Now coming to the excess volume. See, once again we know that dG is equal to VdP minus SdT. So if we differentiate with respect to pressure at constant temperature, then that will be is equal to V. So what we have to do? We have to, that means from here what we can write? We can write dole of excess free energy by dole T, dole P at constant temperature is equal to excess of volume. So excess of volume is nothing but the differentiation of excess free energy with respect to pressure at constant temperature. So this equation, if we take binary solution, this equation I have to differentiate with respect to pressure at constant temperature. Okay. So this what is coming? V or excess volume, that is coming as dole of G excess free energy dole P at constant temperature. So that is equal to, we have to differentiate. So what it will be? Will be RT, then N1 dole of ln gamma 1 by dole P at constant temperature plus N2 dole of ln gamma 2 by dole P at constant temperature. Okay. So this one, if we differentiate, okay, first function, differentiation of the second. So this part we have differentiated. Okay. Then second function. Okay. Then second function, differentiation of the first, but this at constant temperature. Okay. This is differentiation of G with respect to pressure at constant temperature. So that part will be 0. So finally this will be the result for the excess volume. Okay. Now we'll make some discussion. Okay. See, here we have seen that this excess enthalpy, that is equal to your, what is excess enthalpy? Minus RT square, then N1 dole ln gamma 1 by dole T at constant pressure plus N2, then dole ln gamma 2 by dole T at constant pressure. This is the expression for excess enthalpy. Now, this by definition, this excess enthalpy will be equal to, that is the your enthalpy, that is delta H mixing for the real solution or non-ideal solution minus delta H mixing for this ideal solution. This is by definition. Now we know that delta H mixing for this ideal solution, that is equal to 0. So what we can write? Excess enthalpy, that is equal to delta H mixing of the real solution. Now, if here this HE is equal to 0, then what we can think? We can think that delta H mixing for this real solution is equal to 0. But it is not necessarily 0. Not necessary. Not necessary. Why? Because you see here HE, that means excess enthalpy. Excess enthalpy, this is the expression. Okay. Now in the expression, this gamma 1 and gamma 2, that is activity coefficients, they are differentiated with respect to temperature. Okay. Now if these activity coefficients are independent of temperature, then also this part will become 0. Then also H will become 0, but not necessarily that delta H mixing of real solution is 0. Okay, so it is not always necessary. It may happen that this HE is equal to 0 means maybe this activity coefficient gamma 1 and gamma 2 are independent of temperature. Okay. In the same way, this excess volume expression just now we have derived, that VE, that is equal to RT then your N1, then dole of ln gamma 1 by dole P at constant temperature plus N2, then dole of ln gamma 2 by dole P at constant temperature. Okay. So here also we know that by definition excess volume that will be is equal to your, that is mixing of delta V mixing of real solution minus delta V mixing of ideal solution. Okay, and we know that delta V mixing ideal, that is equal to 0. Okay, so if V is equal to 0, then delta V mixing of real solution, that is equal to 0. This is also not necessary. Because in the expression, look at here these activity coefficients are differentiated with respect to pressure. If the activity coefficients are independent of pressure, then also this term will be 0. Then also excess volume will be 0. In that case, it is not necessary that delta V mixing of real solution is 0. Okay, this excess volume is equal to 0. Because of this, it may happen because of this gamma 1 and gamma 2 are independent of pressure. So this VE excess volume is equal to 0 means this gamma 1 and gamma 2 are independent of pressure. If it is independent of pressure, then also excess volume is 0. In that case, not necessary that delta V mixing for the real solution is 0. Hope you have understood. Thank you.